Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. In the last video, I walked through the analysis and design of the common emitter transistor circuit. I even put things together on the bench to test my design, and I showed the effects of changing transistors. Now, if you missed that video, there's a link up in the corner for you here. In this video, I'm going to look at the common collector transistor circuit. I will present its characteristics and go through the analysis and design to get its DC operating point or quiescent operating point into the active or linear region. Then I will go to the bench to see how we did. How well does it tolerate using randomly chosen transistors of the same type? Well, you're going to see that. In this analysis, I will be utilizing the basic model that I introduced in my video on that very subject. If you're not familiar with that model, I would suggest that you take in that video. I've put a link up in the corner for you. I will also be using Kirchhoff's voltage law to do the analysis. If you're not familiar with Kirchhoff's voltage law, I would like to suggest that you take a look at the video that I have on this very topic. There is a link up in the corner for you. Now, I've also provided a go along with the video document for you, which has the whole process in it, along with some extra equations for input impedance and output impedance and the like. You will find a link to this document in the description. Now, I have a very important additional note that you absolutely must remember when creating a transistor circuit that doesn't live by itself. Anything that is connected to the input or to the output of the circuit becomes part of the circuit. They become either current sources or current sinks that can and will change the operation of the circuit, so you need to pay attention to this. Now, if you have questions or comments, please feel free to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe. The purpose of this exercise is to set the operating point of the transistor within its linear active region. Well, what does this circuit look like? Well, the common collector circuit is also known as an emitter follower. It has a high input impedance, a low output impedance. It provides current gain. Now, the current gain is proportional to the DC current gain of the transistor. It does not provide voltage gain. The voltage gain is always less than 1. It is a non-inverting amplifier. That is to say, when the input voltage goes up, the output voltage goes up accordingly. Now, to begin with, we're going to need a power supply. For this demonstration, we will use the power supply voltage of 12 volts. I will call this VCC for our schematic. As a common collector circuit, the collector is considered to be connected to both the input and the output. And in this case, it's connected directly to the power supply. So you might ask, how is this considered to be connected to the input? I mean, the input goes from the input to ground, and the output is from the emitter to ground, and yet this is at the power supply. That is a good question, because the answer is not an obvious one if we're only thinking in terms of DC and continuity. It is because its potential is just as immovable as ground is. Now, it might exist at some voltage above or below ground, but it is a fixed voltage. So from an AC perspective, it is just as much of a ground connection as the ground connection itself is. Now, we need to know the DC current gain of our transistor. We are using a 2N3904, so we'll take a look at the data sheet to get an idea of what value to choose. The data sheet tells us that at a collector current of 10 milliamps, the DC current gain can be anywhere from 100 to 300. So we're going to say that the DC current gain of the transistor is 200. With a little help from the data sheet and picking a number out of the air, our desired collector quiescent current operating point is going to be 10 milliamps. This is IC. Now, we're shooting for the active or linear mode of operation, so we will choose to have the voltage between the emitter and ground to be half the power supply voltage, or 6 volts. This will give us the maximum possible voltage swing for our output. To accomplish this, we're going to need a resistor between the emitter and ground. We'll call this RE. Using the basic model, the base emitter voltage, VBE, will never rise above 0.7 volts. This means that the voltage on the base will be some voltage well below the power supply voltage, so our input needs some sort of resistor to provide current limiting to the base. The other side of this resistor is connected to the power supply voltage source. This provides the bias current to the base. I will call this resistor RB. We want to calculate the needed emitter resistor and the needed base resistor to achieve an emitter voltage to ground of 6 volts with a collector current of 10 milliamps using a 2N3904 transistor, which has a DC current gain of 200. Now, on to the analysis. So let's start our analysis at the emitter because this is what we know the most about. Our first goal is to calculate the value of the emitter resistor. So we'll start with Ohm's law, which tells us that the value of the emitter resistor, RE, is equal to the voltage across it, V sub RE, divided by the current through it, I sub RE. So let's consider the voltage across the emitter resistor. What do we know? Well, we know the desired quiescent operating point for the voltage between the emitter and ground is 6 volts from our design goals. We also know that the emitter resistor exists between the emitter and ground. Therefore, we know the voltage across the emitter resistor, V sub RE, is the same as the emitter voltage, or 6 volts. Now we have to figure out what the current through it is. So what else do we know? Well, we know the collector current is 10 milliamps. And we know the emitter current is the collector current plus the base current. And we know that the collector current is the base current times the DC current gain. After doing a little mathematical magic, we know that the emitter current is related to the collector current with this equation. The emitter current, IE, is equal to the collector current, IC, times the quantity 1 plus beta divided by beta, where beta is the DC current gain of the transistor. So at this point, what do we know? We know that the defined collector current IC is 10 milliamps. And we know the DC current gain beta is 200. Putting these facts into our equation, this gives us the emitter current is equal to 10 milliamps times 1 plus 200 divided by 200, which comes out to be 10.05 milliamps. So now we know the voltage across the emitter resistor, VRE, is 6 volts. The current through the emitter resistor, I sub RE, is 10.05 milliamps by calculation. We can go back to our Ohm's law equation and make some substitutions. We get the emitter resistor is equal to 6 volts divided by 10.05 milliamps, which gives us 597 ohms. Now that we know the emitter resistor value, let's turn our attention to the base circuit. Well, we want to calculate the value of the base resistor. So we break out Ohm's law, which tells us that the resistor value is equal to the voltage across the resistor, V sub RB, divided by the current through it, I sub RB. The problem is we don't know either the voltage or the current at this point. I will start by determining the voltage across it. To do this, I will use Kirchhoff's voltage law around the base loop, which states that the sum of all of the voltages around any loop must be equal to 0. Moving around the base loop, we start at the power supply minus terminal. We move toward the positive terminal. This is a positive change in voltage. We go down through the base resistor, moving away from the positive side of the power supply. So this is a negative change in voltage. We come to the base and then down through the base emitter junction, again moving away from the positive side of the power supply, this giving us yet another negative voltage change. Down through the emitter resistor, yet another reduction in voltage, and returning to the power supply via the ground connection. So let's write the equation which describes this trip around the loop. We have the power supply voltage VCC minus the voltage across the base resistor V sub RB minus the base emitter voltage V sub BE minus the voltage across the emitter resistor V sub RE is equal to 0. So what do we know at this point? We know the power supply voltage VCC is 12 volts. We also know that the voltage across the base emitter junction V sub BE is 0.7 volts. And we know that the voltage across the emitter resistor V sub RE is 6 volts. So let's stick these in our equation. We get 12 minus 0.7 minus 6 minus V sub RB is equal to 0. The only thing we don't know is V sub RB, and we want to know this, so I'm going to add V sub RB to both sides of the equation to get it by itself on one side of the equal sign. This gives me V sub RB is equal to 12 minus 0.7 minus 6. Doing a little easy math, the voltage across the base resistor V sub RB is equal to 5.3 volts. Well, now that I know the voltage across the base resistor, I will turn my attention to the current through it. Well, how do we do this? Well, we go back to the equation which tells us that the base current is equal to the collector current divided by the DC current gain. So at this point, what do we know? We know that the collector current is 10 milliamps per the design goals, and we know that the DC current gain is 200 per our design assumptions. Putting these known values into our equation, we get a base current of 10 milliamps divided by 200, or 50 microamps. Now we get to go back to our original Ohm's law equation. We now know that the voltage across the resistor V sub RB is 5.3 volts, and the current through it, I sub RB, is 50 microamps. Putting in what we know, we get 5.3 volts divided by 50 microamps, so our base resistor needs to be 106 k ohms. We have now accomplished both of our goals. I'm going to go to the bench to see how this stacks up with reality. To put this on the bench, I began by randomly choosing a 2N3904 transistor out of my collection. Then, looking at my junk box, the closest I got to the calculated resistor values was a 604 ohm resistor, which actually measures 606 ohms, to use for the 597 ohm emitter resistor, and a 110 k ohm resistor, which actually measures 110.23 k ohms, to use for the 106 k ohm base resistor. Well, being that these do not match our calculated values, we get to reverse engineer our circuit with the actual values so we can determine what we might expect. To do this, we start with Kirchhoff's voltage law around the loop, which includes the base emitter junction. As before, it looks like this. At this point, the only things we know are that the power supply voltage, VCC, is 12 volts, and the base emitter voltage, VBE, is 0.7 volts. Now, from here, it's going to feel like it's getting a bit complicated, but stick with me until we get to the other side. We're going to take it one thing at a time. And the first thing is the voltage across the base resistor, V sub RB. So we ask, what do we know about it? Well, we know that Ohm's law tells us that the voltage across RB is equal to the current through it, IRB, times the value of it, RB. And we know that, well, the value of RB is 110.23 k ohms. Problem is, we don't know the base current. Well, we'll double back on this. Let's just set this on the shelf for now. We'll come back to it. Now, we ask, what do we know about VRE, the voltage across the emitter resistor? Well, in a similar fashion as with VRB, we know that Ohm's law tells us that the voltage across the emitter resistor, VRE, is equal to the current through the emitter resistor, IRE, times the value of the emitter resistor, RE. And we know the value of the emitter resistor, RE, is 606 ohms. Also, like our VRB equation, we don't know the current through the emitter resistor, IRE. So how can we get at that? Well, we do know that the emitter current is equal to the base current times the quantity of 1 plus beta, the DC current gain. And we know beta equals 200. So now our Ohm's law equation becomes the voltage across the emitter resistor is equal to the quantity, the base current times 1 plus beta times the value of the emitter resistor. Now we get to go back to our Kirchhoff's voltage equation. Now I'm going to do a whole bunch of substitutions here. Watch carefully as it is transformed by these substitutions. VCC is going to get 12 volts. VRB, the voltage across the base resistor, is going to become the current through the base resistor, IRB, times 110.23 k ohms. VBE is going to get 0.7 volts. Well, that's according to our model. VRE, the voltage across the emitter resistor, is going to become the quantity, the current through the base resistor, times 1 plus 200, all times 606, the value of the emitter resistor. Now, take a careful look at this equation. What do you see? You can see here that we have just a bunch of numbers and only a single unknown, the current through the base resistor, IRB. Now, I'm going to do a little adding and subtracting to rearrange this equation so that everything associated with the current and the base resistor IRB is on one side of the equal sign and all of the numbers on the other side. And so then we get on one side 12 volts minus 0.7 volts. On the other side we get the current through the base resistor times this quantity, 110.23 k ohms, plus 606 times 1 plus 200. Now I divide both sides by that big blob that's multiplying I sub RB, so I can get that current through the base resistor all by itself on one side of the equation. This gives me, on the top, 12 volts minus 0.7 volts. On the bottom, we have 110.23 k ohms plus 606 times 201. Do the math, and what do we get? We get a current through the base resistor, of 48.7 microamps. Now we know the current through the base resistor, which in this case is the base current, is 48.7 microamps, and we can turn our attention to the emitter. Well, now that we know the base current, we can calculate the emitter current because we know that the emitter current is equal to the base current times 1 plus beta. And we know that the base current is 48.7 microamps, and we know the DC current gain beta is 200, which gives us an emitter current of 48.7 microamps times 1 plus 200, which comes out to be 9.788 milliamps. We know that according to Ohm's law, the voltage across the emitter resistor, V sub Re, is equal to the current through the emitter resistor times the value of the emitter resistor. And we have an emitter resistor current is equal to 9.788 milliamps, and we know that the emitter resistor value, R sub E, is equal to 606 ohms. So we have the voltage across the emitter resistor is equal to 9.788 milliamps times 606 ohms, or 5.93 volts. Now that we have an idea of what to expect, let's go to the bench and see what we actually get. So here's my little setup. And what do I get for an emitter voltage? Well, we were expecting 5.93 volts, and we got 5.86 volts. That is pretty doggone good. But reality hits. The calculation of these resistor values and the success of our bench experiment all depended upon the actual real-world transistor having a DC current gain of 200. In our case, I just happened to choose a transistor that had a DC current gain of around 200 in my random pick from my junk box. But what happens if the transistor we happen to get doesn't have a DC current gain of 200? The datasheet says it could be as low as 100. That's half of what we used here. It also says that it could be as high as 300. That's 50% higher than what we used here. What happens then? Well, let's try a few other randomly selected transistors in our setup to see what the results are. The first gives me 4.67 volts. I read 5.96 volts for the second. The third yields 6.4 volts. And the last gives me 5.34 volts. Man, these readings are all over the place. How can we deal with that? That answer lay in a video to come on a beta stable design. When this is released, you'll find a link for it up in the corner here for you. Well, don't forget the important note of the effect of circuits connected to the input and or output of transistor circuits. They all become part of the circuit as either the current sources or sinks, and they will affect the operation of the circuit. So, there you have the common collector or emitter follower configuration of the bipolar junction transistor. In the next video, I will be doing analysis, design, and reverse engineering on the common base configuration. If you found this video helpful, please click on the like and subscribe to the channel. Thank you so much for watching. Until next time, Toodle-Oots.